A warm good morning to respected professors, R&D engineers, RF engineers, antenna engineers, research scholars, and beloved students to the webinar on antenna placement analysis using SBR plus solver in Ansys AEDT. And I would like to thank everyone for joining this webinar. And this webinar will be presented by me, Divyashree M, with PhD in RF filters and currently working as an application engineer, high frequency electromagnetics under ARK Info Solutions, the channel partner of Ansys, part of Synopsys now. Ansys stands top in the simulation as it sheds light on filling the gap between imagination and reality in our day-to-day life in various domains. Indeed, Ansys has more than 90% of customer satisfaction worldwide, with more than 6,500 full-time employees and 90 plus offices, with a proven revenue of 2.54 billion USD. Being number one in simulation world for more than 50 plus years, Ansys has made 29 strategic acquisitions and invested more than $5 billion in the acquisitions with the 350 plus technology partners, including Fluent, Apache, Granta, Autodesk, Microsoft, Dyna, Rocky, and many more. And now we are to the core reason, like why do you want to perform simulation? To understand this, let's have a small video clips from Ansys.
What do the world's most visionary companies have in common? A superpower. To see the future with absolute certainty. The power to design, to test, and to predict the performance of the most complex products in the universe, all before a single physical prototype is ever built. They summon the world's most powerful engineering simulation solution, Ansys.
I would like to add some flavors to the video, like why do we go for simulation? The very first reason is one can predict the behavior or the performance of any component or a device or a system virtually before it is brought into existence. On the other hand, if the device or component or a product is not performing well, it can be optimized using powerful Ansys solutions. And by doing so, the time and cost of the product development drops drastically. And if in case a product undergoes a failure, the root cause for the failure of the product can be analyzed in depth using powerful Ansys solutions. And finally, before a product is brought into a market, it has to undergo or comply with certain EMC standards, that is electromagnetic compatibility standards like FCC, ISO, SBR, MIL, etc., in order to ensure the safety of the equipment, the person, and also the environment, which all these things are virtually feasible by powerful Ansys solutions. To perform such powerful simulations, Ansys has simulation portfolio that broadly covers various domains in our day-to-day life. In case of semiconductor, Synopsys and Ansys provide solutions like Redac SE, PowerArtist, Totem, RaptorH, RaptorQU, etc. And when the user want to perform simulations related to embedded systems, CAD-based software packages are provided by Ansys solutions like SCAD Suite, SCAD Display, SCAD Vision, SCAD Artist, SCAD Test, etc. And for safety analysis-based simulations, Medini Analyze for cybersecurity, Medini Analyze for semiconductors can be used by the users. When it comes to structures, Ansys solutions like Mechanical, LS Dyna, Motion Sherlock can be used. Under fluids, softwares like Fluent, CFX, Rocky, Turbo Tools, etc. can be utilized by the engineers. And electronics, which is our laser focus today, has solutions like HFSS, Maxwell, SI Wave, IcePack, MotorCAD, Q3D Extractor, New Hertz, Filter Solutions, AMA 3D Cable, and the AMA 3D Charge. Among this, Maxwell and MotorCAD comes under low frequency electromagnetics, and remaining solutions comes under high frequency electromagnetics. When we are focusing on optical domain, Ansys provides solutions like SPIOS, numerical based FTTD softwares, and also ZMax Opti Studios. When an engineer wants to perform simulations with respect to materials, Granta-based packages are provided by Ansys, like Granta MI, Granta Selector, Granta EduPack, Granta MDS, etc. For autonomous vehicle-based simulations, Ansys has AV Accelerate, that is headlamps, sensors, and autonomy. When user want to perform mission-level simulations, Ansys provides packages like System Toolkit, Orbit Determination Toolkit, and there is a special software for performing sound-based simulations, that is acoustics. The software is Ansys Sound, provided by Ansys. And optimization is a critical part in product design. So that can be done using special software packages from Ansys like OptiSlang, Minavera, Model Center. And moving on to digital twin, which is the virtual representation of any physical asset, so that you can monitor the data for the continuous or seamless processing of processes of the any devices or system. So this process can be done using Ansys solutions like Twin Builder, Twin AI. And we also have 3D design. For 3D design, Ansys provides solutions like Discovery and Space Climb, where you can perform the alterations, change the 3D model at a time and just look for the results instantly. And special feature from Ansys, that is Ansys Cloud Direct, where users can perform simulations over the cloud, which will drastically reduce the simulation time and also the hardware requirements. Yeah. Moving on to Ansys applications, like simulation is ubiquitous. We can find its applications starting from consumer electronics to space. And moving on to high frequency electronic product collections. And first comes HFSS, which is short for High Frequency Structure Simulator, a powerful electromagnetic simulation software from Ansys that is used to design, optimize, and analyze the RF and microwave components like antennas, filters, PCBs, IC packages, connectors, etc. And the second comes HFSS IC, which deals with the simulations that are taking place at multi-physics and multi-scale platforms with respect to the integrated chips. Then we have Q3D extractor, which deals with the simulations to extract the parasitic RLCG, that is resistor, inductor, capacitor, and conductance parameters from the interconnect structures. And special software called IcePack, which deals with the thermal-based simulations with respect to IC packages, electronic devices, and then even power devices. SI-Wave software that been focused on solving these simulations related to signal integrity and power integrity concepts like coupling, interference, ground bounds, and voltage fluctuations. Everything comes under SI-Wave and power integrity. So signal integrity and power integrity with respect to IC and PCBs. As a continuation, we also have EMC Plus, which is used to deal with the simulations related to EMI EMC, like conducted emission, radiated emission, conducted immunity, radiated immunity, and even cable harness modeling, which can be done at the platform level, starting from automotive to aerospace applications. And then Charge Plus, which is used to deal with the simulations that are concerned about charging and discharging phenomenon like dielectric breakdown, electric arcing, and even lightning effects on the aircrafts. To all filter designers, special solutions provided by Ansys are Cinematrix filter and New Hertz filter solutions, where Cinematrix filter can be used to design 3D filters, like complex 3D filter designs that can be with respect to your ceramic filters, SAW filters, cavity filters, etc. And in case of New Hertz filter solution, this filter solution actually deals with the planar filters and also the lumped elements that are being placed on the planar filters, and it is very rapid because it is being integrated with AI. Using Ansys solutions, one can solve simulations starting from nanometer scale to kilometer scale, that is from silicons to systems. When you want to perform simulations at photonic and silicon based based products. Numerical based software packages are available from Ansys. And when simulations related to semiconductor, that is chip level simulations, can be performed with semiconductor packages. And when the simulation has to be performed from meters to millimeters, softwares like SI-Wave, IcePack, Q3D Extractor, and AEDT can be utilized. For hardware level of simulation, softwares like Maxwell, Sherlock, EMA 3D cable, MotorCAD are prominently used. And finally, when you want to perform simulation from nanometer to kilometer in a one powerful software, that is HFSS, which is High Frequency Structure Simulator. Let's learn what is high frequency technology and then how it works, like what is the workflow of high frequency technology. The very first step in starting the simulation is to choose proper solver. Like solvers are the computational methods that is used to solve Maxwell's equation and find out the electric and magnetic fields. So first is HFSS FEM, which is a finite element method, where you have a 3D model that is being enclosed by a radiation boundary. Here, the entire volume is being discretized into smaller tetrahedral elements, and electric and magnetic fields are solved for each individual tetrahedral elements and summed up to get the final results like electric and magnetic fields. And this FEM, HFSS FEM solver can be best suited for complex geometries like antennas, filters, connectors, PCBs, ICs. And then comes HFSS IE, which is the integral equation, which solves Maxwell's equation in the integral form, and it is best suited for electrically large metallic structures like satellites, aircraft, reflector antennas. And we also have SBR plus, which is advanced shooting and bouncing ray solver, which is able to solve the electrically large scenarios like radar cross-section analysis, antenna placement analysis. And there is DDM, which is the domain decomposition method. When you have a huge electromagnetic problem like an aircraft, it will be divided into smaller subdomains, and each subdomains will be taken care by separate computers using a technique called HPC, which is high performance computing, which shares the network processor and memory. And finally, the results are combined and produced to the user. Once your proper solvers are selected, geometry is being created inside the HFSS. And you also provide proper boundary conditions, excitations, the frequency we are going to work upon, and also the fields that you're interested in, like near field, far field, with respect to the antenna behavior. And meshing, once you're done with the geometry, like which is automatic adaptive meshing, your 3D model, this is a simple microstrip patch antenna, that is insert FET map microstrip patch antenna, will undergo discretization of into the smaller tetrahedral elements like this, based on the resonant frequency or your solution frequency that you provide. And after this discretization, Maxwell's fields will be solved based on Maxwell's equation, and it will be summed up, but still there will be field variations happening rapidly at certain regions of the antenna, like corner and edges of the antennas, P point of the antenna. So the antenna, like the solver will start to refine the meshes, like bigger tetrahedral meshes will be replaced by the smaller ones. And again, fields will be solved to reduce the errors in the fields. So this process continues until the convergence criteria is satisfied, which means my current S parameter result and previous S parameter result should not vary that much. Like we set a threshold level to it. And from the S parameter result, we obtain other results. So it comes under post-processing, like we view the current distribution, like at the surface level, volume level, and also the fields, how the field, like near field, far field results. And optimization, once you are not satisfied with the performance of the electromagnetic model, you can go for optimization. Like when my antenna, I'm designing for 2.4 gigahertz, but it is not resonating at 2.4, it is resonating somewhere at 2.8 something. So I can go for optimization for this, where I vary the dimensions of the antenna from the smaller value to higher value with a certain step size, and pick up the best one that I'm interested. And the other option is optimizer, where you can set a goal to the software and the software will work upon it to get your goal. And the next is Ansys customization to suit, where one of the best example is antenna toolkit from Ansys AEDT. You can design antennas within seconds. Like you no need to spend a lot of time starting your antenna design equations, then finding out the dimensions, then providing boundary conditions, excitations, and then moving on to results. This process has been drastically reduced by Ansys, which is a great advantage to all use antenna designers. And then we have multiphysics, which deals with the simulations that combines multiple domains like optical, electrical, mechanical, thermal can come into one picture. Like simulation can be performed at the system level or scenario level or at the mission level. We have certain solvers in HFSS. The first solver is frequency domain FEM solver, as I said before, where the 3D model will be divided into smaller tetrahedral elements and fields will be solved to get the electric and magnetic fields on the geometry. And it is best suited for complex geometries because it is focusing on tetrahedral element meshing. And time domain solver, here it focus on the transient based simulations like EMI, EMC analysis. And frequency domain IE solver, which is best for electrically large metallic structures like aircraft. And for SBR plus solver, which is advanced shooting and bouncing ray solver, it is a best solver for electrically large scenarios like automotive radar simulations, antenna placement analysis, etc. And these are the examples where simulations can be performed inside Ansys HFSS. First is signal integrity and power integrity. And second one is automotive radar simulation. And third is the RF filters, where you can focus on complex TD filters also. And then comes RF core-site analysis in airplane, where two antennas will be placed inside a platform like aircraft, and how the coupling happens, how the behavior of antenna affects each other or with the surrounding platform. And then comes biocompatibility, where you have phantom models from Ansys like hand model, head model, body model. You place your mobile phone with your antenna and check for your SAR analysis, like specific absorption rate, which is telling us the amount of RF energy that is being absorbed by the human tissue. And finally comes antenna placement analysis, where you can analyze the behavior of antenna, how it changes when the environment changes, like from system, like component level to system level to platform level to the mission level. As I said before, antenna simulations are generally taken place at component level. Like I design an antenna at like a single unit cell, and that simulation is taking place at the component level. From that single unit cell, I create an antenna, so that forms an system level design. And then I place this array antenna on a platform like base station, and then check its performance. And finally, take this base station along with this array antenna and put it in the real-time scenario where multiple base station antennas are interacting with each other. And now we are moving on to the antenna placement analysis using SBR plus in Ansys AEDT. The workflow starts like initially we are going to design with PFA antenna that operates at 0.8 gigahertz and analyze its performance like S parameters like S11, that is return loss, then radiation pattern, impedance using Smith chart. And this PFA antenna is then taken to the next level, that is system level simulation, where this has been placed inside a car mirror, and performance of the antenna is again analyzed, like how the radiation pattern changes, how the return loss affects. And this is then carried out to the next level, which is platform level, where we place this car mirror on the body of the car and check for its performance and look for certain parameters like radiation pattern significantly. Let's have a small glimpse of SBR plus. Uh, when there is SBR plus, there should definitely be SBR. Come, let's learn the difference between SBR and SBR plus. SBR is shooting and bouncing ray, which is a traditional method that you launches the rays from a source called antenna, then which is being launching rays on the geometry of the platform. And this is being done by the phenomenon like geometric optics that involves reflection, refraction, and it paints the currents on the geometry. But when you keenly observe, certain regions are only being painted with currents, the remaining regions are not covered by the currents. To solve this issue, some enhancements were made from the traditional SBR method and named it as SBR plus in future. In case of SBR plus, the edge diffraction, that is diffraction due to edges, were considered along with the uniform surface currents that is being given by uniform theory of diffraction. But practically, surface currents are not uniform over the metal surface. They are crowded near the edges and corners of the metal parts. So this correction was made by PTD, which is physical theory of diffraction. And even though these corrections are made, some regions are remaining in the shadow region, like they are not being covered with surface currents. So that was taken care by creeping waves, where they start to creep along the geometry of the metal so that they can paint the currents. So when all put together, the entire geometry is being painted with the surface currents. From the surface currents, electric and magnetic fields are obtained. Now we'll move to demo part of antenna placement analysis. This is the user interface of Ansys Electronic Desktop 2026 R1, where you have menu bar at the top with File, Edit, View, Project Tools, Window, and Help. And you also have ribbon tabs like Desktop View Simulation. According to the ribbon tabs, you will have ribbon icons in your ribbon area. Like when you go to desktop, you will be finding the softwares like HFSS, HFSS 3D layout, Emmet, circuit netlist, etc. And also Q3D extractor, iPack, Maxwell. And below your ribbon tab, you have a project manager window where you will be having details that are related to your HFSS design or whatever design you are introducing into it. And below your project manager window, there is a properties window, which will provide the properties of the uh, electromagnetic model which you are designing here. And now I'll try to introduce HFSS design environment by clicking on Insert HFSS. HFSS design environment has been introduced. Here, this is the design area. This is a design area which has been divided into two parts. One will be your history tree, and other is the 3D modeler window. Under the history tree, you would be having information regarding your coordinate system, planes, and also the 3D geometry, which you have been drawing it in the 3D modeler window. And when you expand this HFSS design, you will be seeing certain nodes that are related to your HFSS, like 3D components, model, circuit elements, boundaries, excitations, mesh, analysis, optimetrics, results, field, port field display, field overlays, and radiation. The very first thing when you start your design is check for the units. By default, the units from Ansys AEDT is millimeter, so we'll just leave it as it is. And the next step is the solution type. So right click on the HFSS design and choose an option called solution type. You'll be able to see a variety of solution type like HFSS with hybrid and arrays, transient, SBR plus, eigenmode, and characteristic mode. In case of HFSS, where HFSS will solve the electromagnetic problem based on FEM meshing, like finite element meshing, where it takes the divides it 3D model into smaller tetrahedral elements and solves Maxwell's equation from it. And in case of HFSS with hybrid and arrays, it combines the HFSS, that is FEM method, with the hybrid, with the other methods like integral equation technique or SBR technique. so that the simulation time drops, and you can also choose this solution type when you're working on the large platform based simulations. And transient is meant for AMI AMC based analysis, and SBR plus is for antenna placement analysis mostly. And eigenmode, you can analyze the features of any resonator, like how my fundamental resonant frequency of a resonator and everything. And then we're moving on to options like network analysis, where network analysis you will be, when you have a device that is two port, my software will analyze the first port and keep the second port matched with the source impedance, that is characteristic impedance. But in the case of composite extraction, both ports will be solved simultaneously. And when you choose modal options is generally suited for microstrip based designs. And for terminal, it is like multi-conductor based transmission lines will come under terminals. And when you click on auto open region, you'll be able to find the boundary conditions like radiation, FEBI, and PML, where radiation is where you create an free space, like you mimic your free space environment for an antenna, and which is generally placed lambda by 4 distance away from the radiating element. And FEBI is a combination of finite element method and boundary integral, which will reduce the computational volume of the volume which is being followed by the radiation pattern. Like when I have a dipole antenna, I don't need an entire rectangular box as a radiation pattern. That radiation pattern, like not radiation, but the radiation box, the FEBI will take up the radiation box arbitrary shape according to your 3D model. That is the greatest advantage with FEBI boundary. And PML, it is generally used to solve the smaller antennas like implantable antennas and also the array antennas. This is all about the introduction with Ansys AEDT. Now we'll start designing the antenna, which is at the component level. To design an antenna at the component level, I go to View, ACT extension, that is Antenna Customization Toolkit extension. So click on it. And click on Launch Wizards. You will be having HFSS Antenna Toolkit. So click on this. Yes, my antenna toolkit has been successfully opened in Ansys AEDT. Here you can find different antenna types like bow type, conical, spiral, dipole, helix, horn, log periodic, etc. But our interest is PFA antenna, which is planar inverted F antenna. So click on planar inverted F antenna. And now on the right side, under the settings of PFA antenna, the very first thing is center frequency. Specify your center frequency for which you want to design your antenna. We are interested in 0.8 gigahertz, so I'll give 0.8 gigahertz as my center frequency. And the substrate details. So I am going to work upon FR4 epoxy. So I'll choose FR4 epoxy and choose my substrate height to be 0.16 centimeter. Once I specify my center frequency and also the substrate height, I click on synthesis. You keenly observe the dimensions of your feed substrate antenna are updated as per your center frequency and the FR4, that is your substrate details. Yes, now your antenna has been generated by Antenna Toolkit. This is the powerful tool which can be utilized by any antenna engineers worldwide. And now click Finish. And we'll close this ACT extension. Now the design antenna has been imported into HFSS design environment with all predefined settings. You no need to do anything. Everything is done by the software itself. Like you can go to boundaries and check for the boundaries. See, planar inverted F antenna has been assigned to be metal, then the feed part and the ground part. And expand your excitation where your antenna has been, PFA antenna has been fed with your lumped port with one of the arm. And analysis, right click on the, double click on the analysis and check for the center frequency, or just right click on it. Double click on it. Once again. ATK solution, you find your center frequency, that is my solution frequency at 0.8. When you are working on broadband and multi-band antennas, you can choose your frequencies like here. You have options in this, like choose your multi-frequency or broadband frequency, give your lower and higher frequencies. And number of passes, maximum delta S, which is my convergence criteria, as I said before in the Ansys workflow, where my present S parameter data has to be very less, like it has to have less difference compared to the previous one. And results, we are interested in 3D polar plot, 2D polar plot, return loss, input impedance, and radiation. The software itself has provided the 3D in infinite, that is created far field sphere, that is infinite sphere for 3D, which is varying all the phi and theta values. Similarly for azimuth plane and elevation plane. And now everything has been kept ready by the software. We'll check for any errors or warning messages. To do that, go to HFSS, click on validation check, and you look every like design settings, 3D model, boundaries and excitations, mesh operations, analysis setup, optimetrics and radiation. Everything is being approved by the software. We can't find any errors or warning messages here, so we'll close it. If you find any warning or error messages, kindly work upon it and then validate once again and then simulate your results. The next step is to simulate. Go to HFSS under your menu bar and just click on Analyze All. Now my HFSS software will simulate my antenna. So we'll wait for the software to simulate the results. Yes, the simulation is complete. And now we are in the return loss plot. So go to marker, and then add X marker and drag your marker to the resonance point, that is at 0.82 gigahertz. And this provides return loss of 39.13 dB, which shows my antennas perfectly resonating at the 0.8 gigahertz. And input impedance, that is my Smith chart. This is the S11 trace, which is closer to your central part of your Smith chart, which shows my antenna is perfectly matched. And the 3D polar plot. This is the 3D polar plot produced by the antenna. To see this polar plot on the antenna, just right click on the plot, show in modular window, and go to HFS, just double click on HFSS design. Now you will be able to see the radiation pattern on the antenna, like how my radiation pattern looks with respect to my antenna structure. Now we'll move on to 2D and 3D radiation, like 2D patterns, like elevation and azimuth plane. The green trace, which is present here, shows that it is the vertical cut of the radiation pattern. Like when I cut the radiation pattern vertically, I'm going to have elevation view. So, which is being given by this green trace, and the blue trace, which is shown here, is the azimuth cut. That means when I cut the when I cut the radiation pattern horizontally, I'm going to have like this way horizontally. I'm going to have the radiation pattern in this way. This is the vertical cut, and this is the azimuth plane radiation pattern. And we'll save the design. This is all about designing antenna at a component level. Now we are going to take this workflow to the next level, which is system level. For this, I'm going to open a 3D modular, like 3D component of the antenna mirror, that is a car, which is also having PIFA antenna inside it. So this is a 3D model, like 3D model of a side mirror of an antenna. That is, mirror of the car, which is having a PIFA antenna in it. So I'll try to open this. When I zoom it and expand the model under my history tree, I'll be able to see FR4 epoxy where my PFA antenna is residing on it, and a glass material and a PEC that is holding the other internal parts of the mirror and the side body of the car mirror. Now, this model has been provided by Ansys to the customers, like it is a ready-made model. When you want to work upon with the real-time examples, you have to get CAD models or the 3D models from the third parties, and then place your antennas on it and work upon it. And now we'll just check for the errors. Go to HFSS validation check, and there are no errors, so we'll simulate the antenna. Second, error with the software. This is the already simulated one of the side mirror of the antenna with following results like S parameters, gain, and everything. And we look for the S parameter, which is my return loss. It is closely resonating to 0.8 GHz with return loss greater than 12 dB. And my gain plot, this is the radiation plot, that is 3D polar plot of the antenna that is being placed inside a car body. Sorry, inside a car mirror. So right click on this, show in a modular window, and go to the design, HFSS design. You will be able to see the radiation pattern of the antenna with respect to the car mirror. When I want to increase the size of this radiation pattern and look with the antenna, just go to field overlays under your HFSS project. Right click on it. Plot fields, you have radiation field. So this is my current gain plot. So increase the scale to 1 and apply and close. And this is the radiation pattern of the PFA antenna when it is placed on the car mirror. Look at the difference. My radiation pattern has been changing. Like earlier it was like a two lobes. Now this has been trying to unite as a single lobe. And this is the radiation pattern of the antenna with a vertical plane and a horizontal plane. Now this antenna has to be converted into a 3D component to make this antenna sit on the car body. So once you have completed this simulation analysis, just Control A, you're selecting all the components present inside the model and right click on it, and you find an option called Create 3D Component, and it will ask for a name. Just provide a 3D component name and give OK, and it will ask for location also. Kindly provide the proper location. and save it. So this simulation is actually happening at the system level. Now we are going to take this car mirror with an antenna to the platform level, that is like a car body. So again, I'll introduce one new HFSS design, that is project. And here, sorry, yeah. Here I'll try to, yeah, I'm just focusing on this level of simulation, that is platform level. I need a CAD model of a car body. So that has to be imported from the design folder, which has been brought from the third party. So I have to go to the simulation, that is my design environment, and look at the modular option, which is present in the menu bar. So click on the modular and import. I'm going to import the CAD model of the car into the design environment. So browse the CAD model from your design location. The CAD model will be with the extension of .sab. So open it. Yes, the CAD model has been successfully imported into the HFSS environment. Now, but look into the history tree. No material has been assigned to the car body. So we are going to assign the material to it, that is a boundary condition to it. Since it is a metal, we'll assign perfect E to the car body. So Control A, where we are selecting entire parts of the car, and right click on it and click on assign boundary and provide perfect E boundary conditions and give OK. Once your boundary condition is finished, the car model has to be work on certain solver. So that solver is SBR plus. To assign that SBR plus, I have to choose proper solution type. So 1 second. Where is HFSS? Here it is. Right click on HFSS design, solution type, and my solution type is HFSS with hybrid and arrays. Only when you opt to this option, you'll be able to see SBR plus while assigning the region. Here it is. Here you have to choose HFSS with hybrid Ansys, hybrid and arrays, and click OK. Make sure your solution types are uniform from starting from component level to system level to platform level, so that there is good coordination between among the simulation environment. And once this is done, and we can go to units. Since we are working upon the large scale platform, I'll change my units from millimeter to meter. And give OK. Yes. Now I need to place this 3D, that is component, which is my car mirror along with the PFA antenna on the car body. For that, I have to specify certain locations of which software understands. So to place that location, I can use coordinate systems. There are two coordinate systems, that is global and relative coordinate systems, where you can find at the center of the simulation domain. You can find, hello. Yeah. Here you can find your coordinate system, that is global, and to have relative coordinate system, you can go to draw and you find an option called offset. So click on it and choose a appropriate position where you need to place your car mirror. So I'm choosing this position to place my car mirror. So double click on it. So under coordinate system, you can see two coordinate systems, that is global and relative CS1. So double click on it, and I'll try to optimize this position because my car mirror has to exactly sit on the car body. So I'll provide values like 0.8. My origin will be 0.8 meters, comma 0.75, comma 0.25. And the binding values are same. So I'll give OK. And this is a position where I want to place my antenna mirror, like antenna along with the side mirror. Now I have to import my or take my 3D component, that is my antenna side mirror, into the car body. For that, go to the Draw tab and you find option called 3D component library. So browse it. Browse from your destination location where you have saved your files, that is 3D component file. Yeah, this is a 3D component of our file which I have saved it recently. So open it. Once you try to insert the 3D component, it will ask for target coordinate, whether you want to make this 3D component sit on the global coordinates or relative coordinate system. We are interested on relative coordinate system, so click on that option and give OK. And you have to just carefully place the car mirror on the coordinate system. Such that it sits on the RCS, that is relative coordinate system 1. Yeah. Now my antenna is exactly residing on the RCS, that is relative coordinate system. And now we have to analyze the results for results like radiation pattern. And that is significantly shows that how my fields are getting scattered or being disturbed by the environment. To have that radiation pattern, we have to first set up the far field, like insert far field setup under the HFSS design. So under radiation, right click and insert far field, infinite sphere. We'll focus on name it as elevation. Where my phi is going to vary from 0 to 90 with a step size of 90. And my theta is going to vary from minus 180 to plus minus 180 to plus 180, and give OK. And check for any errors, like validation check. Yeah, you have to work upon like 3D model is being something is interacting, like it is overlapping with boundaries are overlapping, and also analysis setup. Analysis setup, like we have to provide on what frequency we are going to analyze. So right click on the analysis, add solution setup and advanced. Click on frequency as 0.8 gigahertz. And give OK. We are getting some error with respect to 3D model. Yeah, is it possible to put the antenna inside the car? Car SBR solve it if it will be inside. Yeah, you can place anywhere you want. The thing is, you have to add the location, like provide your target relative coordinate system, and then you can place it. And this is the results which has been solved after placing the antenna on the hard body, which actually resonates closer to 0.8 gigahertz. And 1 second. And my gain of the gain and radiation pattern of the antenna, which looks scattered, like fields are getting disturbed, radiation fields are disturbed by the antenna when it is placed on the platform like a car body. To view this on the 3D modeler window, just right click on the plot. We'll take only one plot and show in the modeler window. And then go to HFSS design. See, this is the radiation pattern of the antenna which is placed on the car body. Now I'll go to the coordinate system and use local coordinate system. Elevation. Okay, when you choose your local coordinate system, you will be able to see this radiation pattern that has been related to your car body.
Divya, can you show them the angles related part where they can tilt it with 10, 15, 30 degree and accordingly
Sure.
gain plot also getting changed. And someone has asked regarding using SBR solver, can we calculate range of our antenna? Yes, for that she has shown you gain patterns. So using that you can have that clear idea.
Yeah, I'll show how the mirror is, when your mirror is swept with certain angles, how the radiation pattern changes. For that, I have to go with RCS1 and I'll add some variable to the angles once again. For this, I have to change the mode of the RCS where I can edit here. Go to mode and provide Euler angle. And phi, I can assign a variable. I'm going to sweep along the phi where I assign a variable called mirror angle. And give the value as 0 degree. And assign variables like I have to sweep the angle from minimum value to maximum value with certain step size. Then I go to optimetric, like optimetrics under analysis, add a parametric, add a variable called mirror angle where I do it with linear step size with 0 degree to 30 degrees with a step size of 15 degrees and add it and give OK and OK then. Now I'll save it and simulate my result. It will take some time to complete the simulation. Till that, I'll continue with my presentation. I hope these simulations are interesting and insightful to all of you. Now we'll move on to Ansys learning resources. Like Ansys Innovation Space, you also have inside that Ansys innovation courses, plenty of innovation courses in various domains, like from electronics, you have solutions to EMC problems, crosstalk on near field coupling. Not only it stops with this, you have broad topics included under the Ansys innovation course. And once you complete this, you will be provided with completion patch. You can add it in your resume so that will be a great weightage for your resume. And then you also have Ansys Learning Hub, where you can take up courses, very useful courses, and work upon your current projects and also improve your insights regarding the topics that has been focusing on current trends from Ansys. And you also have Ansys student version that is free for students to download from the website, where they can work upon projects and you also have Ansys GPT, where you can ask queries regarding your simulation performance, like how when you're facing any issues while performing simulations, you can go to Ansys ChatGPT and you can ask and clarify your doubts. Yeah, meanwhile, if anyone has any doubts, please be open to ask. Or else drop your queries or questions inside the chat box so that I can read and reply to it. We can measure individual patterns, but I want to measure combined pattern. Combined pattern in the sense, like you want it at with all angles of phi and theta. Hello, sir. Hello, Murali Krishna. Hello.
Combined patterns they can also do. The results which we can able to plot individually, we can generate those details in Excel sheet. We have option that we need to just right click on result and export into .csv files. Then once you have two separate CSV files in the same plot, you can import the results so that you can combine both plots together and see the difference. And Lokan is asking, ma'am, could you please plot that range of antennas covering distance at different power? Could you please explain the question?
Range of antenna. Range of antenna generally deals with Friis equations, right?
Yeah,
This transmission equation. Okay.
exactly what he wanted to ask.
Yeah,
Please explain it so that we can
yeah.
give answers accordingly.
Yeah, Lochin, are you here? You can unmute your mic and you can ask. Just we need some clarifications on your questions. Or else, can you retype the question so that we can understand? Yes, instead of Friis equation, we can plot using SBR.
So basically, SPR is actually used for electrical size of any geometry, like how she has shown you here two geometries on one single HFSS design. So as per the size is getting increased, actually it is getting changed. So you can do the same thing. Friis equations also is one of the way. We can do it. There is no any issue based upon the geometry size we are choosing here solver. That's it. So when you are doing two antennas trans-receiving on one HFSS design, so generally we are for that purpose we are supposed to use IE solver, which she has initially shown you various types of solvers available for HFSS. So based upon electrical size of antennas, you can choose the solvers.
Any
So one
questions from
simulations we
participants?
can perform in multiple ways. There is a no any standard. This way only you can perform. You have solvers, different solvers provided to you. Based upon your application, you can choose it. But please consider the electrical size of geometry, and based upon that, you can choose the solvers.
Any questions from participants? Feel free to ask.
Yeah, she has shown you in how the angles, if she are changing, how the pattern is also going to get changed. That part she has explained here.
Combined radiation pattern in the sense you're looking for coupling kind of thing. How two antennas interact with each other. You mean in that
No,
way,
I think
Murali?
he wanted to keep two different antennas and left and right mirrors separately.
Okay.
So you have to uh, plot antennas radiation separately in this case. Then I have explained already. You just have to right click on that and export any one of the
Okay.
radiation pattern in Excel file. And then once you want to check combined both radiation patterns, you can import that extended.csv file in any of the radiation pattern of antennas. Then you can compare both the results.
And
But
we
results
all
you need to plot it separately and then convert into .csv part. That Excel values you will get in all angles and then export into any of the result. Then you can compare. I hope Murli Krishna, you have got your answer. Vamsi Sai.
When it comes to range of antenna, it mostly depends upon Friss equation, that is Friss transmission equation. If there are any method, we'll try to find it out and we'll get back to you.
Okay. Divya, Kasturi, I guess we can connect them and ask them in case if they have any doubts. Okay. Maybe we
Okay,
can do a
Sheetal.
one-on-one if it is possible and see if they have any other doubts or anything. Not 100%, but somehow they got an idea. So maybe
Okay.
Murli Krishna, we can connect with you separately and I can have a call with Divya and Kasturi and have you connected with them so that you can have your query cleared. Okay. Divya
Yeah,
and Kasturi, please.
just
Yeah,
give me
yes,
5 minutes,
Kasturi.
Sheetal.
Sure.
Divya, can you go back to the design where you have plotted radiation pattern? So we'll give a little bit idea
Yeah.
for them so that go to the radiation pattern where you have plotted radiation pattern. Results. Inside the results, gain plot 1 and 2.
Like simple radiation pattern.
Yeah, 2D radiation pattern.
1 second.
Not this one. Go a little bit up. Yeah, right click on this. Export.
To marker table.
No, export below.
Okay.
Export is there.
We have
So
CSV.
you can check it here, Murli Krishnan. You can plot those results in .csv files. Basically, these are Excel sheets. Save this, Divya, anywhere so we can show them. Go back to the folder
1 second.
where you have saved that.
Okay. Yeah, it is here.
Yeah, so you can see it here. These are the files already saved it here. Then go back to the original design, Divya. Let's suppose this is one of the other antenna. For an example, I'm giving you. Then right click over here.
Here itself
Huh.
or to the
Yeah,
other?
here itself.
Okay.
Here itself.
Okay.
Click on import. And you can add that result in
Okay.
the same radiation pattern. Here exactly it will
Okay.
come on the top because we
It is
have
overlap.
already, yeah. So I hope you have a clear idea. This is one of the radiation pattern for left mirror. Same way you plot right mirror. Right mirror, once you are plotting, do the same thing. Like export it first, and any of the
Yeah.
either it is left or right, you check it. You can see now she has imported. So likewise, you can have a comparison. I hope now it is 100% clear. You said it not 100%, but you got an idea. We have shown you how to do that.
Yes, Sheetal.
Yeah, Divya.
Yeah, I think you can continue.
Yeah. Okay. I guess they still have the question. Murli Krishna
This,
still have the question. So yeah, Kasturi and Divya, you can take it up.
This
yeah,
is
I
Yeah,
comparison
he
of
wants
two
to connect later.
neural patterns. Coverage is
yes.
different. That's what I looking. No, can you explain your question first? Because you're talking about radiation patterns only. And you're asking
Average,
combined radiation patterns. We have shown you combined radiation patterns.
combined radiation pattern in the sense like you're focusing on the same antennas or different antennas because radiation pattern differs from antenna to antenna.
Otherwise, Divya will connect separately.
Yeah,
Divya, you
Yeah,
can
that
share your email address so that if they have any query, they can connect with you via email. If required, you can connect with MS Team as well.
yeah, sure, Kasturi. Yes, sir, sure. I'll share my email address, sir, so don't worry. Any other questions from participants?
I guess Divya, there are no more questions. I'm just putting your email ID
Okay.
in the chat box. One sec. It's Divya.money, right? Yep.
Yeah. At ark.info. Sorry, arkinfo.in.
Yes. So we have put Divya's email ID in the chat box as well as our answers, the generic email ID wherein you can send us any topics that you want us to give presentation for. Either Divya, Kasturi, they'll be more than happy to take out their time and give the presentation. So please let us know if you want us to give you any presentation or anything. You can mail us at answers@arkinfo.in, or in case if you have any queries also, you can mail us at answers@ark.info.in, and we'll connect you with Divya and Kasturi. Okay, by saying so, I guess there are no more sessions. So this is a series of sessions that Divya will be doing. So the same time next week she'll be having the second session. We will be sending the invite for the second session in some time to all of you. So it will be a continuation of Divya.
Yeah, the webinar will be on 5G millimeter wave antenna array design. So kindly join, which is focusing on 28 gigahertz design of antenna. So I think it will greatly help those who are working on with array designs.
Okay, so this is
Yeah.
the session on is on array design. So we hope to see you on our second session as well. So it's a series of session of 3 webinars. The first one is today. The second part is happening the next week at the same time. A mailer will be sent to all of you. So we hope to see you in that session as well, where Divya will be presenting us an amazing session as today. Okay, thank you so much, Kasturi, for joining us today, and for taking up all the queries as well. It was really lovely to have you in the session. Thank you so much,
Thank you.
Divya, for the amazing session, and thank you so much everyone for joining us, for your queries, for the interactive session. We were glad to have you all.
Thank you all. See you on the next webinar
Have a good day.
series.
Bye.
Yeah.